free to give the talk for.
Thank you. And thanks to John and Rich for the great talk. So my name is Jerry Xuan. I'm a grad student at Caltech, and I'm giving this talk on behalf of Jingwen. Um, Jingwen couldn't make it here today, unfortunately, because she came down with COVID, but feel free to definitely do reach out to her with questions if you want to learn more details later. Um, all right, and also bear with me for any mistakes. So this talk is about characterizing the 3D architecture of a planetary system with a transiting hot Jupiter. So, sorry. Oops. So the first hot Jupiter, Beta 51 Peg V, was discovered almost 30 years ago. And today we have a lot of ideas about how these objects form. Um, it is possible under some circumstances for them to form in situ, that is where they are. Um, but these objects have orbital periods of a few days. So a more natural process might be that these objects migrated from further out in the disk inwards to where we observe them today. And there's many ways to look for clues on the origin of hot Jupiters, and one way is to look for companions to them. So these could either be planetary or stellar companions, and different formation mechanisms can predict different properties of these outer companions. For example, if you form in situ, then you don't need a companion at all. If you have a companion, it could be nearby, and it might not be in orbital resonance. In disk migration, where planets migrate inwards through interactions with the disk, you might predict companions near the hot Jupiter to be in orbital resonance. And finally, in the more dynamically hot view of high eccentricity tidal migration, the idea is that the hot Jupiter initially started further out and its orbit got excited. And as it got very eccentric, it experienced significant tidal damping from the star to both circularize its orbit and also move it closer in. So this theory obviously requires a distant and probably massive companion. So what Jingwen has been working on as part of her thesis is to cross-match the TESS object of interest list, which are potential transiting planets discovered by TESS, with the Hipparchus Gaia catalog of accelerations, which indicates the presence of outer companions on orbital periods larger than roughly a few years. So she has built this sample of objects. Some of them have really high acceleration, which are towards the upper right of this plot. And these objects, some of which she has imaged with Keck 2 to reveal close stellar companions. On the other hand, there are also some systems with low acceleration amplitudes on the bottom left that might be consistent with these systems having substellar or planetary companions. And in this talk, she's focusing on one specific system, TOI 1271. So this is a hot Jupiter that was first uncovered with radial velocity data many years ago. In 2006, it was published. And here are its properties. It has a moderate eccentricity. And interestingly, this system was one of the systems that showed a significant astrometric acceleration. Of note, this hot Jupiter is also transiting, and the star it's transiting around is actually on the subgiant branch with a radius of about 2 solar radii right now. So, that didn't work. But Jingwen and collaborators proposed for follow-up RVs because there might be an outer companion indicated by the astrometry. And so they proposed for Keck high-res time to continue to monitor the radial velocity since 2020, and combined with the older RVs from high-res and LOD, they are actually now able to constrain the orbital period of this outer companion. It's roughly 15 Jupiter masses, and so it's on the border of like a giant planet and a brown dwarf, essentially. So this is interesting. And on the right here are the phase-folded RVs for both the hot Jupiter and the outer companion. Another way to probe the origin of hot Jupiters that's been popular is with the stellar obliquity. So this is basically saying what is the angle between the stellar spin axis, n star, and the orbital vector of the hot Jupiter n0, and O. So this angle can be constrained with the so-called Roster-McLaughlin effect, which is you monitor the radial velocity of the transiting planet as it transits, and there's different distortion shapes that can be mapped onto different sky-projected obliquities. So in this case, they've proposed for Keck KPF time, and over the course of about 5 hours, we're able to measure the sky-projected obliquity to about 20 degrees. Of note, this is only the sky-projected obliquity, lambda, so to get the true obliquity, psi, you need 2 more angles, and one of which is available because we know the planet is transiting, so the inclination of the planet's orbit is constrained. So Jingwen then went ahead and tried to measure the inclination of the stellar rotation axis. This can be done in many ways. One of the ways is to combine the V sin I measured from spectra. So we have obviously high-res and KPF spectra for the star, in addition to the rotation period. So this can be obtained from missions like TESS. And in this case, they found evidence for rotational modulation on the order of 23 days. Combined with a V sin I, this gave the stellar inclination axis, which is around 90 degrees. So putting all this together, the true obliquity can be measured. And it's consistent with being a low obliquity system. It's not... this plot shows a lot of hot Jupiters with measured obliquities. Most of them are actually sky-projected obliquities, so there is a uncertainty there about the true obliquity. But this system fits well with the cooler stars, which have been observed to have more aligned orbits with the star. And this is thought to be because these cooler stars have deeper convective envelopes, which are more efficient at damping any initial misalignment. Which brings up a good point, which is that for these cooler stars, the dynamical history of the hot Jupiter can be partly erased by later realignment. And in this system, the star is a subgiant, so there's definitely time to do this. Ongoing work, which I am partially involved, is to actually measure the 3D orbit of this outer companion. So I said there's a RV period for it, and when combined with astrometry, which measures the sky plane velocities, you can, in some cases, constrain the full 3D orbit of the outer object. And once you know that, then you would know if the outer planet and the inner hot Jupiter are misaligned or not, which is a very interesting probe of dynamics as well. At the moment, there is not a great constraint on the inclination of the outer companion, but so far it's consistent with being 90, which means it's consistent with being aligned to the hot Jupiter. But future RVs could help improve this a little bit. Right, so here is a schematic of possible ways to further test the hot Jupiter origin story. If you have a mutually inclined companion, then it could induce Kozai leadoff cycles to excite the eccentricity of the proto-hot Jupiter and cause it to tidally migrate. On the other hand, if the companion and hot Jupiter are nearly aligned, then this mechanism doesn't necessarily work. But as I mentioned, a big caveat here is that tidal realignment from the star could later erase some of the dynamical history that you're trying to probe. However, this is still a really interesting system. It's one of the only systems with measured true obliquity for a hot Jupiter, and some constraints on the 3D orbit of the outer companion. So a lot of people have said, okay, hot Jupiters may form via high eccentricity migration, but there's not been a system that completely fits that yet. So this is a step towards finding more systems like this and constraining the origin of hot Jupiters. And finally, she said she would like to thank 2 team members who provided tremendous support in this work. So thanks very much.